So we're here for lecture 7 on the course Proof Complexity as a Computational Less. Today we are going to talk about the resolution proof system. Maybe our final lecture focused exclusively on resolution. We are going to study width, which is another complexity measure of proofs, looking at the size of clauses in the proofs. Why do we care about width? Because it turns out that this complexity measure helps us understand other complexity measures, such as length or size. And this is something that we will see today. Something that we won't see today is, I don't know if you remember from the very first lecture, we talked about space measures, where basically we'll give a more formal definition later when we get there in the course. If I give a self-contained presentation of a resolution proof on the board, keeping everything that is needed for the derivation on the board, then clause space is the number of clauses, max number of clauses I need at any point. Total space counts total number of literals. It turns out that if you have a good handle on width, then this can also help me to understand not only length, size, but also clause space and total space. We'll hopefully see this later in the course. In order to prove what we want to prove today, we will introduce two technical tools that are maybe long overdue. First, I'll introduce a somewhat stupid extra rule for resolution, and this will be the weakening rule. Remember that the resolution proof system we had, okay, so let's just write it down for completeness. In resolution, we have the resolution rule that says that for C or X and D or not X, we can derive C or D. The weakening rule basically says, well, from any clause C, I can derive a weakened clause C or D. Normally, when we talk about resolution refutations, we don't allow weakening. Today we will. It's kind of a stupid rule. It's only said that if you already have C, then I'm allowed to weaken it by adding clauses. This will turn out to be useful. We'll see this shortly, but let's just make sure that we agree on the following, that I can actually add this weakening rule without loss of generality. So suppose that I have a resolution refutation. Here it is, pi, it refutes F, and it uses weakening. Then from any such refutation, I can transform it to another refutation pi prime without weakening in at most the same length. So the length of pi prime without weakening is at most the length of the refutation with weakening. This is not hard to see, since we're going to see the proof is just by induction over the derivation, by forward induction. Since we're going to do a lot of these proofs going forward, no pun intended, let me just write this out a little bit more carefully than would otherwise be the case, maybe. So the proof is as follows. So we have this pi. This is a sequence of clauses, C1, C2, up to CL. From this, I will build pi prime, which is C1 prime, C2 prime, up to CL prime. I will maintain the invariant that for every I, Ci prime is just a subset of Ci. Okay? And I will maintain the invariant that every Ci prime is either derived with the resolution rule or is just a copy of a previous clause. Now, resolution doesn't have a copy rule, but clearly in the post-processing step, I'll just remove all copies. And then one other thing that could happen is that maybe actually in this pi prime, I will derive contradiction several times. Let's just stop the first time we derive contradiction. So I claim if I can just turn this clause by clause, from Ci to Ci prime where we satisfy this, and the derivation would be like a substructure, then we should be good to go. Then this tells me that without loss of generality, I can throw in weakening because we can remove it later. And that will allow us to be very relaxed about weakening going forward. Okay, so the induction is kind of straightforward. What's the base case? Well, the base case is if Ci is an axiom. If so, I just set Ci prime to be Ci. This is clearly valid. Okay, for the inductive step, suppose that I have Cj being weakened to give Ci by weakening. Then I will just set Ci prime to be Cj prime, which I already constructed. Okay. And finally, suppose that we have Cj, which is C or X. We have Ck that are D or not X. And they were used to derive Ci, which is C or D. Obviously here J is less than I and K is also less than I. Now I have three cases, basically. So suppose that X is in fact not a literal in Cj prime. In that case, X is already gone, and it's not so hard to see that I can just set Ci prime to be Cj prime. If not X is not in Ck, then I copy let Ci prime be a copy of Ck prime instead. If both of these cases apply, then flip a coin. Otherwise, we let Ci prime. So otherwise, we just let Ci prime be the resolvent of Ci, J, and C prime J and C prime K. And we know now that this will then be Cj prime or Ck prime, except we remove both X and X bar. And now we just need to check that all of these steps are valid and that we always maintain this invariant. But this is basically the proof. And also, we haven't introduced, now you see like any other measure you care about, width will be the number of clauses. The space measure that we will also talk about later, and most other properties of proofs are maintained by, I'm just extracting a subproof. So for most aspects of resolution that we care about, if the weakening step helps you for whatever reasons, then throw it in, and then you can remove it later without affecting pretty much any proof complexity measure that we care about. Are we happy with this? And so basically we'll have a few more proofs like this today, arguing by forward induction over the derivation, and then I'll probably just say by forward induction. And in future lectures, I also say by forward induction, and then it just means a case analysis like this. Good. The next thing that we need, now we already talked about, but we're going to do it a bit more carefully today. We're going to talk about restrictions. So our restrictions typically get the letter rho, and this is just a partial truth value assignment. For notational purposes, it will be convenient. So two pieces of notations that I will use. Rho will map variables to true or false, 0 or 1. And then it's pretty standard to say, well, if something is not in the domain of rho, then rho leaves it unchanged, or we sometimes just write that rho maps it to star. just as a convenient piece of notation. We can also think about rho. Sometimes I will think about rho as the set of literals that are set to true by rho. So if rho, maybe suppose that rho of x is true, rho of y is false, and rho doesn't set anything else, then I will sometimes it will be convenient to say that rho is the set x of y. Because that will then allow me to use set notation and say that a literal is like in the restriction, which just means that it sets the restriction, sets this literal to true. Okay? So now I want to talk about what happens. We already did, actually, when we did the interpolation proof, we already looked at resolution derivations and we applied restrictions to them, except I didn't tell you what was going on. So let me talk about this more carefully now. So for any clause rho, any clause C, that's a C, here comes the restriction, here's rho. C restricted by rho is the following. There are two cases. Suppose that rho satisfies the clause, which I'm introducing a bit more notation on the fly. Okay, actually I'll be a little bit, let me write it this way. So if rho intersects C, note that we agreed that a clause is a set of literals and restriction is also a set of literals. So this notation makes perfect sense. Sometimes I will, just to be extra clear that I'm picking out the literals of C, I might write things like this, lits of C. If rho satisfies C, then I just put a placeholder and say this clause is the trivially true clause. Otherwise, what the restriction does is it removes all falsified literals in C. So all literals not L such that L is in rho. Okay, and now suppose that F is a CNF formula, then F restricted by rho is just the conjunction of the restricted clauses, except our convention is that we'll remove trivial clauses 1. And similarly, if pi is a sequence of clauses, it's a derivation, then the syntactic object so far, pi restricted by rho, is just listing all the clauses, the restricted versions of them. Okay, this makes sense? And now the claim we want to make is that for resolution, and indeed for most well-behaved proof systems, if I have a refutation of f, or in fact any derivation of something from f, a derivation pi, and I hit it with rho, the restriction rho, I apply the restriction rho to it, I hit it with rho, then pi restricted by rho will be the corresponding derivation from f restricted by rho. Okay, so let me write down the formal proposition. It's going to be something like the following. Suppose that pi is a derivation of f, not necessarily of contradiction, could be any clause A. And suppose that rho is a restriction, and to make this meaningful, we want to say that rho doesn't satisfy A because then it's not so fun. Then I claim that if you just look at the sequence of clauses pi restricted by rho, then that is a valid resolution derivation from f restricted by rho of A restricted by rho. possibly with weakening. Okay. This I'm not going to prove, but I'm just going to say you do this kind of proof. Yeah. So this is a purely syntactic statement. I just can take this derivation and then just apply the restriction clause by clause. I filter out anything that is satisfied. What remains will be a valid resolution derivation, except possibly for weakening steps. And we will be mostly interested in this when A is the empty clause, so that it is a refutation. But now, now we know already from the first proposition, which we can call proposition 1, that, well, once I have a derivation with weakening, I can just do a post-processing step and remove the weakening. And in fact, so this notation, sometimes we will allow ourselves to be a little bit sloppy with notation. This might actually be sometimes the resolution derivation that you get from first just applying the restriction and then cleaning away weakening steps in the obvious way. I'll try to be clear, but if I'm a little bit sloppy, then that's because in view of these propositions, it doesn't really matter. What I will do, I'll do a proof by picture. Let's see if I can do that. So here is a formula F consisting of X or Y, not Y or Z, W or not Z, not W or not Z, not X or not Y, Y or Z. And here's a resolution refutation, which will give the name pi. Okay. Now wait, what? Yes. Now I want the restriction. I'll apply to this the restriction y is set to 0, y is set to false. Let's see what happens. Well, this clause goes away. It's satisfied because y is false. This clause also goes away. It's satisfied. Y is false. This clause gets trimmed to just being x. And this clause gets trimmed to just being z. Okay. So what we have now, this, and this, and this, and this is f restricted by rho. And now we know that if we just apply the restriction, the same restriction to all the clauses in the proof, then we should get a valid refutation. Now, it's kind of a small toy example, so it's not so fun. We get rid of all the y's right away, so it's a little bit boring. But we can still verify that this is valid, except that you see here, the first step is now that we're just going to take x, and we're going to say, well, if x is true, then definitely x or z is true. This goes away, so this is just the weakening step. Similarly, here we say, well, if z is true, then definitely not x or z is true. This step is unaffected, and then you just resolve the rest. Okay? So this is a small, stupid example of proof by picture that restrictions preserve resolution refutations. Now, suppose I applied proposition 1, just to be clear what would happen. What would the cleanup be? Well, the cleanup would be, we'd go over the proof and we'd realize that I don't need to weaken here, so I'll just get rid of this and only get x here. This I cannot change. Here, again, I would just say I don't need to weaken, I'll just copy z. So meaning that, in fact, this will be the same clause, this will be the same clause. And now I will realize that, oh, but here I have z, here I have not z, and I will just, by resolving them, I get contradiction. This was this case over here. And then I realized that, oh, okay, I can stop here. So the resolution derivation we will get after cleanup will just be the clause Z. These two clauses, W or not Z, W, not W or not Z, you resolve them to get not Z, and then you resolve Z and not Z to get contradiction. Proof by picture. Are we happy with this? Because now I am basically trying to move on, and from now on I will consider it justified to use weakening whenever I feel like it. Whenever it helps me, I'm going to use weakening. Whenever it hurts me, I'm going to consider weakening steps being removed. Are we happy so far? Hopefully someone's happy.
So
yeah,
I just have a question for proposition 2. I think you just said that it's true for like all well-behaved proof systems.
Yes.
For what proof system is this not true?
Well, yeah, for instance, if you take subsystems of resolution that try to model what SAT solvers are doing,
okay,
then it's not true. So the following claim you can say, like, make a proof system that models faithfully enough what a SAT solver could do. Okay, then it's not true that you take any SAT solver proof and you hit it with the restriction that you get another legitimate SAT solver proof. That's not true. But that is, we'd have to talk about how SAT solvers work.
Yep. Okay.
Okay. But basically, I mean, this holds for resolution. It's not hard to see that it holds for polynomial calculus. It holds for Canning planes. I mean, it holds for, the Frege systems, Shirley-Adams, as well as most. But sometimes this notation will entail also this obvious, well, I have to fix up some things. So, but for most well-behaved proof systems, modulo fixing upping, this is true.
Okay.
Good. So now width. The width of a clause is just the number of literals in it, which, since I consider a clause to be a set of literals, I can just write as set size of C. The number of literals in C. And now it's straightforward to define, well, suppose I have a CNF formula, then I just look at all the clauses in it, and I take the maximum. That's the width of the CNF formula. And similarly, if I have a derivation, I just also look at all the clauses in it and take the max. And that's the width of the derivation. And now, a piece of notation that we will use is the following. If F is a CNF formula, if A is any clause, I can write the width of deriving A from F, assuming that this is possible. If this is not possible, then this is going to be infinity. Actually, it's going to be infinity, I guess, with this measure also. But we're just going to look at all the possible resolution derivations that do derive A from F, and we take the minimum width. Right? And this is the width of deriving A from F in resolution. Just to denote, just to recall that we have a similar definition. I don't remember if we've written it down. The length of deriving F from A would be exactly defined in the same way. And where this R means that, I guess, we're minimizing over resolution derivations. Okay. One thing worth noting, though, is that it's not necessarily the same pi that achieves these minima, right? This is something that we'll talk about later in the course. Okay, so this is what we want to study today. From now on, let F be an unsatisfiable KCNF formula. Meaning that width of F is, let's say, equal to or at most K. I don't care so much. I don't necessarily, just for today, K is not necessarily a constant. Let's just say it's the width. Okay? And let it be over n variables. So lowercase n, today and also in other lectures, unless otherwise stated, it's often when n is floating around and a CNF formula is floating around, lowercase n is often the number of variables. Okay, so what do we know? Well, here's an obvious observation, but still it's important to keep in mind. However hard you try to be stupid, in a real resolution refutation without weakening, you just can't go above the number of variables in the resolution width. So width is at most the number of variables. I think I'm not going to prove that one. Here's but I gave it a number apparently. This is observation 3. Let me write down a slightly more interesting observation. Observation 4. Actually, let's agree also, just to avoid typing, that whenever I write pi, unless there's context, pi is always a refutation of S. This will allow me to be a bit more compact. So I claim that the length, suppose that I have a refutation of F of width at most W, then I claim in general resolution, then without loss of generality, the length of pi is at most n to the big omega of W. Okay. So, refutation in small width, a narrow refutation, is by necessity short. Okay, what's the proof of this? Well, the proof of this is basically just count the total number of distinct clauses over n variables of width W is, well, there are n variables, meaning 2n literals, and you have W choices. Okay, and now you can say, well, what if the width is smaller? Okay, good, let me throw in a 1 here just to choose to omit the variable. So clearly, the total number of distinct clauses of width at most W over n variables is this. And in a general resolution refutation, you never need to repeat the clause. Why would you? Okay? So this is a rather obvious upper bound. So the main topic of today is something slightly less obvious. So, okay, let me rephrase this. You could rephrase this to say, well, if there is a narrow refutation of F, then there is also a short refutation of F. This is one way of saying this, but it's slightly imprecise. Let's note that actually it's the same derivation. Any refutation of pi of F that is narrow, that very refutation, unless it's doing something immensely stupid, that very refutation also has to be short. Okay? So narrow proofs are short without loss of generality. Now, what we're going to talk about today is the famous paper, the celebrated paper by Ben-Sasson and Wigderson, which says short proofs are narrow. So, very informally, and we'll spend today on making this more precise, the theorem says that if there is a short refutation of F, then there exists a narrow refutation, meaning a refutation in small width of F. Okay? This is what we want to prove today, and the paper by Ben-Sasson and Wigderson is the journal version is from 2001, short proofs on merit. Note, by the way, I should mention also that this argument fails if we're interested in tree-like resolution. Because we said that, oh, why would I ever repeat clauses? Well, tree-like resolution has potentially very good reasons to repeat clauses, namely that you can only use any clause in a resolution step only once. And indeed, this argument fails in a major way for tree-like resolution. It's known to be false. I don't think we will cover this. But are we happy with this? Okay, so and we're happy with this example, and I'm getting rid of it. So our goal now is to make this precise as we can. So now, oh, I should have said one more thing over here, just a convenient piece of notation. Suppose that rho is just it just sets a single literal L to true. Okay. Then sometimes instead of writing things like pi restricted by rho, just because it's easier to see, I might just write pi restricted by, whoops, that looks suspiciously much like a rho. I meant to write an L. Okay, so I will write something like, pi restricted by x. What is this? This is the pi restricted by the restriction rho that only has domain size 1, namely it sets x to true. Okay, I could, or if I had the energy, I would write something like this, but we want to type as little as possible. So are we happy with this type of notation? You should always be happy with anything that minimizes typing. I mean, that should be our goal as mathematicians. Okay, good. So let me do two lemmas. With notation as above for f and everything, just to save typing. Suppose that f is a CNF formula and a is a clause such that when I take f, I hit it with the restriction setting x to true, and from this I'm able to derive a, and I can do this in width at most w. Suppose this holds. Well, in that case, what happens when what happens morally when I run the same derivation, if you wish? We'll make this precise in a second, but I only run it on f. What can we say? You sort of unrestrict, so you should pick up not x, right? So you should get something like a or not x. And if there's any justice in the world, what should this refutation width be?
W plus 1.
It should be w plus 1, except that just to be a little bit careful, it's going to be the max of w plus 1 or w of f. If I worked really, really hard, I could get rid of this, but I'm going to carry this around just for convenience. Actually, this is a little bit ugly. Let me move this. W, the width of f, a or x, that width is max width of f or w plus 1. Okay. What's the proof of this? Maybe let's just say how would you prove this? Well, fix whatever refutation is here. Okay. Then I want a derivation of this thingy. I should say possibly with weakening. Okay, actually let me write down. So basically the proof is going to be the following. One, I just list all clauses in f. 2, I list all clauses D or not X, where D is a clause in this refutation over here. Okay. I just list all the axioms in my formula, and then I take the derivation here, except that I just tag on not X to all the clauses. Clearly, the final clause is going to be this. Clearly, the width is okay. I mean, here I'm picking up W of F, here I'm picking up W plus 1, and then you just have to verify that this is a legitimate resolution refutation with resolution derivation with weak A. And I was planning to cheat you on that. Are we happy with this? Okay, simple lemma. So the next lemma is also not rocket science, but it's going to be extremely useful for us. Suppose the following holds. Suppose I can prove to you that if I set X to true and try to refute F with this restriction, then the width is at most W minus 1. Okay, and suppose when I set X to false and try to refute that the width is at most W, then what can I say about the width of refuting F? Okay, I claim that, well, in that case, we get max of the width of the formula and W. Okay. Meaning, what I'm saying is that suppose I find a good variable X, and suppose for one way of setting X, I get width W, and for the other way of setting X, I actually gain an additive 1, then that is enough to actually show that F itself can be refuted in width W. We can like ignore W of F, it's not going to play any important role. Okay? You want to see the proof of this, or is it blindingly obvious?
Yeah.
Okay, I agree. I just want to, you know, we're having some small talk while I'm cleaning the board. But I mean, it's kind of, you know, you're gonna, any suggestions? We don't have that much on the board at this point.
Yeah, I mean, it's immediate from lemma 5, no?
It's immediate from lemma 5. Okay, good. Let's, it's indeed true. So let's just verify it.
Here we will be like X, not X, and then it's just
So clearly, my derivation is going to be the following. So proof of lemma 6. So first, I use lemma 5 to derive not X in with max of W, lowercase w and uppercase W of F. Okay. I just, you know, there is some refutation that refutes this. If I just unrestrict, then I will pick up not X in with W. Right? Okay. Now I resolve not X with all C and F such that X is in C. Okay? What does this derive? Exactly, like when I've done this, this will give me the clauses F restricted by not X, the clauses that are affected by this restriction. But note that these clauses I already have. So at this point in time, now I have access to this formula. Okay, and I think we know what to do now. I mean, we're just gonna. I mean, so now we just run the refutation of f restricted by not x in with w as claimed. I mean, this is an assumption. Okay, so we're good. Are we happy with this? Because now basically for all of Ben-Sasson and Wigderson's, we'll do a few theorems, okay, 2 theorems and 2 corollaries, and we're just going to apply. So basically, the game plan is going to be find a variable x that is good to restrict, argue that we can gain an additive 1 in one of the restrictions of x to true or false, and then just lose lemma 6 in some kind of clever inductive manner. Okay, that's the plan. So let me maybe keep the theorem statements over here. Let's first do a theorem for tree-like resolution. This is going to be for tree-like resolution. The claim is that the width of refuting any formula f is upper bounded by, well, the initial width, because the interesting part is, like, in particular, if the formula is minimally unsatisfiable so that you can't remove any clauses, then this is kind of a pretty clear upper bound. Plus the 2 logarithm of the shortest tree-like refutation of f. Okay, so basically, and think of the way to think about this. Let's think about Bayesian formulas for k fixed, because that's mostly the setting we're going to have. So you can sort of mentally remove this. Then this says that in tree-like resolution, the width scales like the logarithm of the length. Okay? So if I have a somewhat short tree-like resolution refutation, then I can refute the formula in width logarithmic of that. The interesting thing, though, is to turn it around in the other direction. This is what is most useful. Namely, in tree-like resolution, just by massaging this expression, it follows that the length of refuting f in tree-like resolution is at least 2 to the width of refuting it, well, minus the initial width, but this is usually a constant. Okay. So as soon as I have any non-trivial width lower bound for my formula, I pick up an exponential improvement in the size or length lower bound. Okay. Does this statement make sense? Okay. So the proof is going to be by induction. I'm going to do induction over a parameter b and the number of variables that it holds that if there's a tree-like refutation of f in length at most 2 to the b, then the width of refuting f is at most the initial width of f plus b. Okay, this is my plan. And I'm going to do this by nested induction over b and the number of variables n. So my base cases are going to be, well, B could be 0. Okay, suppose that B is 0. What can I say about the length of the refutation? It has length 1. That's really interesting. There are pretty few. I mean, a resolution refutation contains at least one clause, and that's the empty clause. So the only possibility is that the empty clause is actually in the formula, which I guess could be the case. It's not a terribly interesting formula, but it's a legitimate case. And then, of course, I don't need to list the whole formula. Well, I could, I guess. Actually, I have room to list the whole formula, but I don't necessarily need to do this. I mean, this refutation has width 0, which is definitely less than 0 plus the width of it. Okay, so this is okay. Suppose that the number of variables in my formula is 1, and it's an unsatisfiable formula. What does this formula look like? Well, in that case, f is x and not x, if it's unsatisfiable. Not that many choices. And in that case, I can just do this derivation, which has width 1, which is smaller than width of f plus whatever b is. Are we happy with the base cases? They're kind of a bit stupid, but so by induction, suppose now that this holds. This holds for all b prime that are smaller than b, and it also holds for the value b and for formulas that have fewer variables than n by induction. So basically, we have, we're filling in. Here is our inductive. We're like filling it in this direction. Let's see if I can. Was this a good idea? Here's the n dimension. Here's the b dimension, and we suppose we have it for all cases up to here. And now we're looking like at. Is this true also for formulas that are refutable in length at most 2 to the b, and they're exactly over like n variables? Make sense? So let's look what the derivation looks like. Well, it's a tree-like derivation. It ends with contradiction. That's true for most resolution derivations. And the final step has to be, some variable x that is resolved. Right? So let's say that this is the case. And now it's tree-like. So actually, I have one derivation down here, and I almost, I said it's tree-like, so let me adjust that so to make it possible to make it tree-like. Let me call this subderivation pi x, and this I want to call pi naught x. This is what the derivation looks like. And now I know by tree-likeness that this is all of pi. The length of pi is clearly the length of pi x plus the length of pi naught x plus 1. Right? Which means, in particular, that one of these guys is shorter than 2 to the b minus 1. Okay, so let's say without loss of generality that, which one did I want to pick? So the length of this guy is less than 2 to the b minus 1. Okay, but now we're done. Because let me note now what happens here. So pi x restricted by setting x to false refutes fx, right? And pi naught x restricted by setting x to true is a refutation of pi with x to true. Right? So let's work on this guy first. So here we can win because this one is short. So by the lemma, by the inductive hypothesis, sorry, I know that the width of f restricted by x, the width of refuting this is width of f, at most width of s plus b minus 1. What can I say about the size of this one or the width of this one? Well, not much. I mean, this could have been a super small guy. This can be very large. But I do know that the width at least didn't go up. And I do know, I do know that the size didn't go up. The length didn't go up. Plus, how many variables does this formula have compared to f? One fewer.
One fewer.
Okay. So by the inductive hypothesis, at least I don't get any gain. I have the same b, but it still holds that since definitely the length of the derivation is at most 2 to the b, by assumption, I mean this is the assumption about this whole guy, then the width of refuting f restricted by x set to false is at most the initial width plus b. Okay, but now we're done. By lemma 6 now says that the width of refuting f is at most the width of f plus b. And this is what we want. Okay. Question, does this mean that short proofs are narrow? Let's see what happens. Like what happens when you apply lemma 6? Well, you're basically, the way we did lemma 6 is you're going to take 2 copies of the proof and concatenate them. So worst case, actually, every time you're doing lemma 6, you're going to double the proof size. Okay? And this is potentially going to happen quite a large number of steps. So actually, we do get a narrow proof in the end, but a priori it could have blown up exponentially. And in fact, this is known. It's known that such an exponential blow up can. Worst case, this does happen. This is Ben-Sasson in 2009 exhibited an example where you get such an exponential blow up for tree locus. Okay. Good, that's for tree-like resolution, but most of the time we care about general resolution. So let me now state what we know for general resolution. For general resolution, we get something like the following, that the width of refuting f, which is again a KCNF formula over n variables, is less than the initial width of f plus, here goes, 8 times n. Let me write down a concrete expression first. I'll take the minimum length of refuting f. I take the natural logarithm of this. I multiply it by 8 times n, where n is the number of variables, and then let me take a square root. Okay, if you don't want to memorize this, this is basically width of f plus big O of n logarithm of the length of refuting. Yeah. The reason I'm writing it in this way, just it's interesting to see that these are not. I mean, these are not galactic constants or anything. It's like it's a reasonable number. Still, it's kind of a little bit of an ugly expression. I don't know if it gives you any insight. At least in order to remember it, you can look at like what is it that you've written in here. So I claim that this is kind of what it says here is log 2 to the n. Okay, you're taking the square root of log 2 to the n times times some logarithm if we don't care too much about, we don't care about which logarithm it is, right? They're all the same. So this is kind of the upper bound we get, which is the geometric mean of the worst case refutation length you could have and the actual refutation length. I don't know if this is meaningful, but if nothing else, it can help you remember this ugly expression. Maybe, or maybe not. As for tree-like resolution, the really interesting thing is when you turn it around, which gives us corollary 10, which is something that we're going to use a lot. So the length of refuting f is, again, just by massaging this, and let me now skip the constants and just write down the asymptotic expression. The length of refuting f is exponential in big omega of the width of refuting f minus the initial width, which is often a constant, so often you can ignore this, square divided by the number of variables n. Now, please note that this is not the number of holes or pigeons or something. This is the number of variables. Okay. So what does this mean? This means that if I can prove a width lower bound, suppose that the initial width is somewhat small. Typically, it's constant or at most logarithmic or something like this when we want to use this. So suppose the initial width is small, we can ignore it. Then I get the refutation width squared divided by the number of variables. So essentially, if the refutation width is square root number of variables or even square root n log n, I don't get anything. Then I just get a polynomial. But if I can push the refutation width asymptotically above square root n log n, then I have a super polynomial. And if I manage to push the refutation width all the way up to linear, then I get n squared divided by n, and exponentially in that, then I get an asymptotically optimal exponential lower bound except for constant factors in the exponent. Okay, and now my apology to you is that all the suffering we had during the first lectures for Satin and for pigeonhole principle, we'll just try to basically in an hour prove both of those lower bounds result using this. And this is in fact like using this corollary and proving with lower bounds is a way in which you can get most of the lower bounds on resolution length that are known. Not all, but most. Okay. In particular, but I don't, or at least I don't know how to do the clique coloring lower bound in this way. Also, very clearly, you could not get anything for clique formulas in this way because the refutation width for a number of reasons. I mean, also for the clique formulas are large width, I guess, but yeah. Also, they're morally. I realize now that I probably have something stupid on record from last lecture saying that they have refutation with k, which doesn't quite make sense because the formula has with n. But basically, morally speaking, okay, how am I going to get out of this? Morally speaking, we know that if you look at the decision tree, you basically just need to explore potential k cliques, and sort of you're only operating on k literals at a time. So morally, the width upper bound is k, and morally also the width lower bound is linear. So like for clique, you're like completely screwed. You won't get anything from this.
So you can get 2 to the k from this.
Yes, by supposing that then we have to massage the clique axiom form clauses a bit, but we could do that probably. Yeah. Yeah, you can, right, yes. If we like allow ourselves to play a little bit with the formula, you could get maybe something like that. Okay, so I wasn't planning on doing the full proof. Because now we're just going to get calculations to do this. But I was going to hand wave the proof to you. So sort of, I'll give you the highlights of the proof, and then we'll take a break, and then we'll try to use it. But basically, this highlight of the proof is going to be find a good variable for which good things happen, then maneuver into a position where we can apply lemma 6, and then it's going to be some kind of inductive argument, maneuver into a position where you can get through your inductive step by appealing to lemma 6, and then you're good. That's the high-level plan. Okay. The low-level plan. I should say one more question that is natural to ask is like, okay, but is this the right bound? I mean, can't we get a bound like this? This looks much nicer. So in fact, this is morally speaking the right bound. So there's a paper by there's a paper by Bonnet and Maria Luisa Bonnet and Nicola Galesi, which exhibit formulas of bounded width that have so constant width, and the refutation width is square root the number of variables, and still they have very short proofs. And that gets very close to almost all the way up to the bound where this would kick in, and still you don't get anything. So like, except for maybe some log factors or something, this is like, the way it is stated here, you cannot improve. And we will hopefully say something about this later in the course. Okay, so now let's sketch the proof. So let's fix a refutation of f. And let's observe that without loss of generality, the length of f is, well, we didn't talk about this so much, but like a worst case upper bound is 2 to the n plus 1, which is, in any case, it's much smaller than e to the 2n, where e is the base of the natural logarithm. As like, without loss of generality, the proof is not worse than this. If it is, I throw it away and I pick a better proof. And again, it's this k. F is a KCNF formula. It's unsatisfiable. It's over n variables. Just writing this down so that we're on the same page. So let me now pick a parameter d. That's going to be 2n natural logarithm of n. This is the way to think about this. Is it looks somewhat similar to this. So this is sort of the width we can shoot for. And let me also set a to be 1 minus d over 2n raised to the power of minus 1. And let's observe that this is actually larger than 1. Just because d can't be too large, because the length can't be too large. Like square root, this is the logarithm of this is much smaller than 2n. So 2n times 2n square root, d is smaller than that, so d divided by 2n is not 1. So this is something positive. Wait, what did I? Yeah, so this is meaning that this is positive but not too large, so this is smaller than 1, and then you invert it, so it's something larger than 1. Sorry, I'm messing this up a bit. Let me say that a clause D is that if it's wider than we would like. In particular, the width of the clause is greater or equal D. So if we can prove the following, then theorem 9 follows. So suppose that G is a KCNF formula over n prime variables, because we're going to use this as an inductive setting. And suppose that pi prime is a refutation of G with, okay, I'm introducing a little bit of notation on the fly. Let me write it and then explain what it means. Suppose that the number of fat clauses in P prime is less than A to the B. So let's just say that fat pi is just the number of clauses in pi such that the width is at least D. Okay. For any refutation, we count the number of fat clauses. Suppose that pi prime is a refutation that doesn't have too many fat clauses, or too many. I mean, it's most A to the B, for A being this thingy, and B is a parameter over which we will do induction. Then I claim that the width of refuting, G, is at most K, which is the initial width, plus D, which is the width we're shooting for, which we don't quite reach maybe, plus B minus 1. Okay. So now I claim that if we get this lemma, then we get theorem 9. And basically the reason is the following. Again, look at this refutation of F. And note that the length of pi, the refutation of F, let me actually say, okay, that the number of fat clauses in pi is, well, less than the length of pi. Let me call L to be the length of pi. Which in particular is less than A to the A logarithm of L plus 1. This is not an equality, this is a less equal. That means that once I have lemma 11, I can just set B to be the A logarithm of L plus 1. And I don't know. I mean, then you just calculate, and you get that in that case, B is actually going to be, like, you do the calculations and you realize that B is at most 2n ln L. Okay, you need to do a page of calculations, which we have in the notes, and now you just put this together and, like, you get this A. You get 2 times this, and then if you pull in the 2, it becomes a 4 times 2, that's it. Not very much fun happens. Are you buying this? We can do more fun stuff than these calculations, maybe? You have the full calculations in the notes. Okay, so now I want to say maybe one more thing, like how are we going to do the induction? So there are a few base cases. The base cases in my notes are a little bit messy, and that's because I'm shooting for this beautiful bound with no additive nothings. I wanted to, like, pick out a constant 8 here, and then you have to work a little bit. And like if you do the trivial base cases, then you'll pick up some additive 1 or 2 here. And obviously that's aesthetically not so pleasing. So I have a few weird base cases to make sure that things don't start growing too early. Let's ignore these base cases. The base cases are fine, hopefully. Or else you'll find, or maybe they're not, and you'll find bugs in my notes, but you know, hopefully not. It's something like this. Okay, so the induction step is more fun. So the name of the game now, I already tell you, we want to use lemma 6. And you're sort of seeing, I mean, here is the induction, right? We have the number of fat clauses is at most a to the b. If the number of fat clauses are not too large, then we get this. So we somehow would like to decrease the number of fat clauses, because then by induction we'll get the width to decrease, and then we'll apply lemma 6 and you will finally get a break. That's somehow like. Okay. So notice that this formula G that we're talking about, it has 2 to the n prime, at most 2 to the n distinct literals. How many literals do we have in fat clauses? Well, every fat clause has at most d literals, and there are fat pi of them. So that means that some literal occurs just by counting in d over d times fat divided by 2n clauses. Okay. So what I want to do now is set that literal to true and hit the, so suppose that literal, some literal, let's say that this literal is x. Then pi restricted, or maybe I called it pi prime, restricted by x set to true, that's a refutation of x, g with x set to true. And the number of fat clauses is, well, I remove this many clauses. They just vanish when I set x to true. So I get 1 minus d over 2n fat clauses, which is 1 over d to the 2n times at most a to the b, and this is a raised to the power of minus 1, so this is a to the b minus 1. And now we're going to play the same game. That means that if we took g and set x to true, then we get a to the b minus 1 fat clauses. So by the inductive hypothesis, we're going to get the refutation of that guy in k plus d plus b minus 2. Okay. For pi prime restricted by not x, I don't know anything, except that I know that there's one fewer variable. So by the nested induction, at least I get this bound. Okay, and now use lemma 6 and then we're done. This is what I wanted to say about the, I mean, and the rest is basically, I mean, I'm cheating you on the calculations, but they're not so fun. So again, you will notice that the way I'm constructing the narrow proof potentially causes an exponential blow up, and it was open for quite some time whether this is inherent also for general resolution. And finally, in 2016, Neil Tappen had a paper saying that, yes, also for general resolution, this exponential, there are formulas which have short proofs and also narrow proofs, but if you take the short proof and you make it narrow, then you get an exponential blow up in length, and this is inherent because all narrow proofs have to be very long. this is where I plan for us to have a break. Any questions before we take the break? Then let's have a break. So we are back after the break, and we proved Ben-Sasson and Wigderson, the famous size with lower bound, or at least we made it plausible. And just to say that if you have little time and you want to do as many resolution lower bounds as possible, or if you want to give a modern treatment of this material, then you do basically what we did during the first lecture now. You establish the size-width relation, and then for most resolution lower bounds, your recipe will be the following, that you look at a formula. You have one problem. If f is not constant width, then you might need to do something. In particular, just getting ahead of ourselves a little bit, note that the pigeonhole principle formulas are not constant width. And yet we're going to use them for this, so we need some kind of tweak, and you can do it in a different way. Actually, for the pigeonhole principle formulas, there are two problems. With this one, but suppose you deal with the width problem, and you somehow turn your formula into KCNF formula. This can be done in different ways. And in this representation, you prove a strong lower bound. Okay. Then, if your width lower bound is good enough, then you just say, well, the length has to be exponential in the width minus the initial width squared over the number of variables. Now, your second problem is if the number of variables is very large, which here, actually, for the pigeonhole principle, the number of variables will be n squared. So that's another problem. And let's see how we're doing on time. Maybe we'll have time to fix this, both of these things. But this is sort of the recipe, how you can do most of your proof complexity lower bounds. And if someone gives you like a new formula for which you want to prove a resolution lower bound, chances are you can do it with the Ben-Sasson and Wigderson recipe. How do these bounds typically go when you want to prove with lower bounds? Well, you look at your formula f, and you study the clause variable incidence graph representation of f. Okay, what is this? Well, you get a bipartite graph. The left set will be the clauses. The right-hand set of vertices will be the variables. And now I just have to specify the edges. And edges, you're going to have an edge x c if the variable x appears in C. Note that we're throwing away information about the sign here. If x or x bar, so not x, appears in C, we draw an edge. So clearly, from any CNF formula, I can turn it into a bipartite graph. And then I want to argue that if this graph is a good expander, if it is well connected, then we're going to get a width lower bound, and then we're going to use Ben-Sasson and Wigderson. What do we mean by good expander? There are many different notions. The notion that we're going to use now is bipartite boundary expander. So let me say that a bipartite graph G, left set of vertices U, right set of vertices V, edge Z, it's an S delta boundary expander, or an S delta unique neighbor expander, if all subset of left-hand side vertices, not too large, of size at most S, where S is the expansion guarantee, then the set of unique neighbors of U prime on the right is at least delta times the size of U prime for some positive delta. The larger the delta, the better the expansion. What are the unique neighbors? The unique neighbors of a set U prime is all the vertices on the right-hand side that are neighbors of U, but every V has only one guy in U prime to which it is connected. Okay? So this is the notion of expansion we're going to focus on. Now, it's not so hard to prove for resolution and also for some other proof system that if I take a CNF formula and I just generate this graph, and if I'm so lucky that I the clause variable incidence graph for f is a bipartite boundary expander, then we're whole. Then we get a width lower bound, and then we get an exponential length lower bound, and we're done. The problem is, more often than not, the CNF encoding is messing up, is not faithfully reflecting the structure of the formula. For instance, for Satin, we will never get expanders. Okay? And why is this? Well, if you think about Satin, we know that if we had a vertex with incident edges x, y, and z, we had a parity constraint to say that this parity should be odd. What is this going to be? Well, this is going to be 4 clauses, right? It's going to be the clauses x or y or z, x or not y or not z, not x or y or not z. Messing up probably, not x or not y or z. I think I got it right. And the problem is that in the clause variable incidence graph, these are going to be 4 different vertices with exactly the same neighbors on the right. That just seems wrong. Yeah. So I would like to say, no, these are like, these are not 4 clauses, this is one parity constraint. Also, when we talk about pigeons and holes, and the pigeonhole principle, now we don't really care about individual variables on the right. We somehow want to argue about pigeons being sent to holes. And so for every pigeon, there are n variables saying which holes it goes to, and for every hole, there are n+1 variables saying whether some pigeon is there. And it's somehow, if you're thinking about the hole, it's natural to collect all variables mentioning that hole. And say these variables are all characterizing what goes into this hole. Also, for the pigeonhole principle formula, if you remember the lower bound we did in the first lecture, we're not looking, when we're doing the lower bound, we're not looking at arbitrary truth value assignments. We're looking at matchings. And then we took these matchings and we translated them to truth value assignments. We could also consider truth value assignments that are not partial matchings, but they would just break our lower bound technique. What I'm getting to in a roundabout way is that this representation is not good enough for us. We're going to refine it ever so slightly. So we'll talk about the generalized clause variable incidence graph that will be guided by our understanding of what the formula looks like. So from now on, we're going to have a CNF formula, and I'm going to write it fancy style F. Let's see if I can write the fancy style F. Curly F over a set of variables, which is going to be curly V. And, or actually, I'm going to maybe do it down here. Let me actually write down. So what we can do here is that we can partition all the sets of clauses, the CNF formula fancy style F. We're going to partition it into a special set E, and then M sets of clauses. These are going to be Fi maybe. Okay. Somehow, the way to think about this is that for Satin, for instance, we would just collect the parity constraints and we somehow bundle them together. And we also divide the set of variables into variable sets. This is not necessarily a partition even. I'll define the overlap for a partition of V to be the max over our variable X for the number of sets VI such that X is in VI. Okay. So I'll partition all the clauses. I will also chop up the variables, mostly partitions, but not necessarily. But if a variable occurs in several different variable sets, it's just going to be a constant. Think of the overlap as being some small constant. And now I'm going to have, so now these are going to be my left-hand side. This is the left-hand side. these clause bags. This is the right-hand set. Okay? And then I'm going to have an edge from Fi to Vj if the variables in all of the clauses, some variable that appears in any of the clauses in Fi is in Vj. Okay?
What was E again?
And E is very mysterious at this point. E just vanishes. Very unclear, actually. Okay? And let me just refer to this as a generalized clause variable incidence graph. Where does this partition come from? It comes from us. Because we understand the formula. And we like, with a Zen-like understanding, we say, I think this is a good partition. Okay? For instance, here is, suppose you have this formula consisting of these 10 clauses. As we will see soon, this is probably not a very good idea, but suppose someone tried to say, okay, F1 are these 3 clauses, F2 are these 3, and F3 are these. And then we're having these variable sets. We see by, just to double check if we're on the same page, the overlap here seems to be 2 because X appears, Y appears there, and W appears here, and all the others appear only once. So from a CNF formula, we could get some kind of graph like this. Okay? And now, we're going to play a game on, so basically, getting a little bit ahead of ourselves, I want to argue that I will be able to get a resolution lower bound if I can build a graph like this. Like once I've done my partition, it's clear what the edges are. I mean, they're just defined once I fix the Fi and the Vj. So if I can find a partition so that this graph is an excellent expander, plus the edges have a certain property, which I'll get to in a second, we'll play a game on the edges. And if we can win the game on all the edges, then we're going to have a resolution lower bound. Let me tell you what the game is. The game is the exciting resolution edge game. Okay. How do you play the resolution? So relative to a structure like this, a generalized closed variable incidence graph, the resolution edge game okay, let me give a notation for this also. I will tend to refer to this whole thing as an FVE graph, where we somehow assume that F and V come endowed with these. We kind of know what they are. So I'll just use this piece of notation to somehow write down that we know exactly this. Okay. So the resolution edge game on FVE is the following. Well, we have to play it on an edge. So it's played on this with respect to the filtering set E. So E will enter the picture in a second. So for an edge, Fi, Vj, the game is the following. It's first, the adversary makes the first move. Adversary chooses a total assignment alpha such that it has to satisfy all clauses in E. So E is somehow deciding which truth value assignments make sense. Okay, getting ahead of ourselves a little bit, what would E be if we're doing pigeonhole principle lower bounds? It would typically make sure we have matchings. Okay? So therefore, you have to satisfy E, otherwise you're like out of bounds. Our sort of the court we're playing on are satisfying assignments for E. Okay? And now we're playing on this edge, and we, the good guys, we're the satisfier. So we modify alpha on Vj to some alpha primes. Okay, and now the satisfier wins if alpha prime satisfies Fi, plus obviously, and we already talked about this, it has to satisfy E. Because otherwise it's not a valid assignment. Okay? The satisfier wins the edge game on this particular edge if the satisfier has a winning strategy, regardless of what adversary plays. The satisfier wins the game on the graph if the satisfier wins on every edge. Make sense? Except, like, why are we doing this? This is another question, but yeah. Okay, so I want to give you one more. Let me write down one more definition. We're going to play this game in a second over there. So actually, you can, while I'm doing the next definition, we're going to play this game on edges. So you can think about winning strategies for either the adversary or the satisfier. But
is the edge chosen adversarially, or?
I mean, if we want a lower bound, you have to be able to win on any edge. But we're just going to illustrate the game by playing on certain edges. So if you, so you win, the satisfier wins the resolution edge game on this graph if the satisfier wins on every single edge in the graph. Okay? So let me now say that this graph, FVE graph, let me call it, it is a resolution expander if the following holds. I want some parameters. It's an S delta E resolution expander. If firstly, I want it to be an S delta boundary expander. Right? I mean, by this definition, we have it. Once I've defined my partitions, I get a graph. I can ask, is this an S delta unique neighbor expander, yes or no? This is my first condition. And the second condition is that the satisfier wins the resolution edge game. On all edges. The resolution edge game with respect to E. That's why I'm carrying this notation around. And let me tell you what I want to prove now. So this is also in Ben-Sasson and Wigderson essentially, except it's all the lower bounds in Ben-Sasson and Wigderson in a common framework written by myself with Vlad and Miksha. So let me say, or let us say, that for a CNF formula, curly F, if there is a good way of partitioning the clauses and dividing up the vertices so that we could get a resolution expander, let's say that the CNF formula admits a resolution expander. I mean, clearly there might be good or bad ways of doing it. Let's say there is a good way. There is a way of taking F and building a resolution expander from it with parameters S delta. Okay? So then my claim is the following, that if the CNF formula F, if it admits an S delta E resolution expander, then the resolution refutation width is at least the expansion factor delta times the expansion size guarantee S over 2 times the overlap, which I forgot to say. If it admits an S delta E resolution expander with overlap L, then, and you should think of, now the point is you should think of the overlap as constant, delta will be a constant. So, and we're going to try to push this expansion size guarantee to linear. So this is going to be a linear size closure. Okay, this is what we want to prove. So what we want to do in the time that remains today, I definitely want to try to prove this. And then, depending on how much energy and time we have left, the question is then, will boil down to like, okay, good, fine. How do I build resolution expanders for from Thakin formulas? How do I build resolution expanders for pigeonhole principal formulas? And let's see a little bit how much energy we have. Okay, but what I was planning on doing now is to play the. I was planning on playing the game, just to see if we sort of understand the game. Okay, let's play on this edge. Okay, and we want to figure out whether the adversary wins or whether the satisfier wins. Did you have time to figure this out? So here the problem, like you should not, clearly someone was trying to build a graph and didn't know how to do the partition in a good way. We do have an obvious problem here, namely that U and X are not in this set. So it's kind of clear that we can never win on this edge because the adversary will just play any assignment that satisfies E. Say I'm playing Y false or whatever, and then make sure to satisfy this clause and violate one of these two. And then I'm allowed to change the assignment or W or Y, and clearly that's not going to help me to flip. Like I'm allowed to change the assignments of these variables only, and I should make all of these clauses satisfied. So I think we agree that this is a loss for the satisfier, this is a win for the adversary. Okay, kind of a boring example. Okay. What about this? Okay, so the adversary might play any total assignment that extends. Let me set U false, W false. Let me set Y false, and actually Z also to false. Is this a legitimate assignment to play? Yes, because Y is false, so it's the filtering set is good. And now the problem is that we are again violating. Wait, I'm copying the wrong assignment, sorry. No, yes. U false, W false, Y false, Z false. Presumably I have a.
First,
what am I violating?
you assigned X.
I'm not assigning X, which makes me a little bit concerned. I don't care so much, actually. So I claim the adversary can play anything like this. Okay, let me just see why. So firstly, okay, what are the variables we can play with? These two. Okay, except note that I cannot change Z. And Z is false. Meaning that I cannot change Y either, because if I would flip Y to true, then I'm violating E. Okay, so I'm stuck with the value of y, and I'm stuck with the value of w. So if you look at F1 under the restriction that y is false and w is false, and probably also that u is false, let's see what I get. So that clause vanishes, but w is false, y is false. So I get x, u is false, I get not x. So now I'm supposed to set a very clever value to x that satisfies both of these clauses. That's going to be really hard. Okay, so we lose. We, the satisfier, loses on this edge also. What about this edge? Now you can kind of tell it would be boring if we lost on this edge also. So now we clearly, now the satisfier wins, right? Sort of. But why? Okay, so we're given an adversarial alpha 3 such that alpha 3 of E, it satisfies this clause. And this is all that we know. And I know that I can change X and Y. I would be stupid to change Y. That doesn't feel safe, but I can play with X. In fact, alpha prime of X, I'm going to look at what alpha 3 is, and I'm going to play that X should have the value that alpha 3 assigns to Y or Z. This is a valid play, yes? Okay, and now I claim that I win. And the reason for this is, well, these clauses encode exactly that X is the OR of Y and Z. Let's see if that's true. It's hopefully true unless I screwed up my signs. These clause says that if X is false, then Y has to be false. And if X is false, then Z has to be false. So if both of these are false, then definitely, like if X is false, forces both of these to false. Okay. Sorry, did I do it the other way around? No. And now suppose that X is true. Well, X can only be true if one of these guys are true. So X is false, forces both of these to false. X is true, forces one of them to true. This is exactly this. So therefore, playing this will satisfy all of these clauses. Note that I don't care about F1, F3. Couldn't care less. Only we're playing on this edge. And I'm not messing F3. So this was a good edge. And I want all of the edges in my graph to be like this. Does this make sense? This is like a key definition. So like if we should talk more about this game, then we should do so now. Yes?
You said what are the formulas that are well-known that admit an S delta E resolution expander?
So we will, if we have Satin will admit this. For the all flavors of pigeonhole principal formulas, I will massage them a bit, and then we'll get.
Okay.
So the spoiler alert is Satin will probably do it. It's very straightforward. For the pigeonhole principle, what we're going to do is we'll take the whole formula and we're going to hit it with a random restriction. Namely, for every pigeon, we just say something like, actually, I remove from you all holes except 5. You can only go into these 5 randomly chosen holes. All the other ones are off limits for you. And I do this for all the pigeons uniformly at random. Okay?
Mm-hmm.
So now it's clear. I'll get what's called a graph pigeonhole principal formula. And now the width, the wide axioms were the pigeon axioms. So they now go down to width 5. If I do this randomly and you do the calculations, this will be an excellent boundary expander.
Okay.
Okay. And now for the now my question is like what part of the formula is the different FIs? What part is the filtering set? Well, for the pigeonhole principle, like every vertex over here would just be a singleton clause, namely the clause that says that pigeon I goes somewhere.
Okay.
Just a single clause. Pretty much everything else goes in the filtering set and sort of says, whatever you're doing, please argue in terms of partial matchings. Okay, and what do I do over here? Well, I identify every vertex Vj with a whole j. So all variables xij for j fixed are going to be in here. So the overlap is actually going to be 1. Okay, and now we're going to say, okay, but wait, you hit the formula with a restriction. Yes, I did, but what happens, it's not so hard to see that since restrictions maintain refutations, suppose that there was a short pigeonhole principal formula refutation, and I hit it with the restriction, it doesn't grow larger, right?
Mm-hmm.
Okay, so if I take my beautiful formula and I hit it with the restriction, and for this restricted formula I get an exponential lower bound, then definitely that bound holds also for the original formula.
Yeah.
Okay, so that's what we're going to do for pigeonhole principal formulas. For Satin, we kind of also said what we're going to do. We're going to have parity constraints over here. And now actually it turns out that here you just, every edge gets its own vertex over here. And it's just a Satin formula, we don't need to filter. So E is the empty set. Okay?
Okay.
That's what's going to happen. And then, but basically all we need to do is write down the details in what I told you now, and then verify that these graphs are indeed S delta E resolution expanders, and then use this, which we haven't proven yet.
And then use Ben-Sasson and Wigderson for that.
And then, so that gives us an excellent width lower bound, and then we use Ben-Sasson and Wigderson. Done. Exactly.
Mm-hmm.
But we are so comfortable with Ben-Sasson and Wigderson now. I'm not, you know, as soon as we get a linear width lower bound, it's like, oh, clearly, guys, we're done. Let's go. But yeah, then we're going to apply it. Okay. So what I want to do now is to prove this. I'm running a little bit out of board space, but let's see. In fact, we might prove this twice, because it turns out that the reason I'm setting it up in this way is we're going to do polynomial calculus lower bound. So we're switching, starting from next lecture, we're going to work on polynomial calculus. And part of it is we're going to see a very similar machinery, except for some crucial twists that will make it, so, okay. Getting a little bit ahead of ourselves, sort of morally speaking, in this game, the adversary goes first, and then we see what the adversary did, and then we get to flip on VJ, and then we should win. Then we get a resolution lower bound. So we're going to define polynomial calculus carefully next lecture. It's going to turn out that polynomial calculus lower bounds are harder. We're basically going to get polynomial calculus lower bounds if we can switch the order. We have to commit first, and then the adversary gets to set all the other variables. If we can still win, exactly the same winning condition, then we have a polynomial calculus lower bound. That's going to require a proof, and we're going to make it formal. Okay, but this sort of, in a very, very concrete way, this is not a characterization of lower bounds, but it tells us sort of that resolution bounds are easier than polynomial calculus lower bounds in a very concrete way. Okay? So do you remember this structure thingy? I might, or maybe let me maybe start over here. So I'm going to define a progress measure from all clauses mapped to the natural numbers. So for every clause, mu is going to tell me basically, if I come to you and I say, hey, I have a resolution derivation from f, and I derive the clause c, and you're trying to assess how impressed you should be. One good thing to do is to apply the mu measure. And if mu is small, then you say, well, anyone could have done that. And if the mu measure is high, then you say, wow, that's cool. Could you show me the proof? Yeah. So mu will have the following three properties. That if A is an axiom in F, then mu of A is small. So in particular, if someone comes to you and says, from this formula, I derived one of the clauses in the formula, then you say, yeah, right. Very impressive. The second property is that if from C or X and D or not X, you can derive C or D, then the measure of C or D, I mean, this is more impressive maybe than these two, but not too much more impressive. We have something that is called subadditivity. So the measure of this clause is at most the sum of the measures. The measure of the resolvent is at most the sum of the measures of the two premises. Okay? And finally, if someone comes and tells you that I proved contradiction, then you're going to be impressed. You're going to say, if it's larger than S, I mean, and S is large, S is actually going to be this S. Suppose I'm able to, again, it's just a mathematical function from clauses to natural numbers. Suppose I define to you a measure mu with these three properties. Then I claim the following. Claim D. For any pi that refutes F, there exists a clause C in pi such that C is like moderately impressive. Somewhere between S half and S. Okay. And this is this should be obvious. I mean, axioms start out being constant impressiveness, and you cannot at most double at every resolution step. So as long as you're staying strictly below S half, you're never going to get to S. But contradiction has complexity larger than S. So the only way you can get all the way up to this is that at least once you're hitting this interval of size like S half. Does this make sense? Okay, great. Then the next claim is going to be that if mu of C is some sigma, which is at most S, then the width of C is at least delta times sigma over L. And L is this guy, and sigma is this guy. Okay, so for any moderately impressive C of impressiveness sigma, the width of C is actually expansion factor delta times sigma divided by the overlap. And now, clearly we have this. because I'm just plugging in that we're somewhere at least S half at some point in the refutation.
Do you really want the open interval there for claim B?
I think so. I mean, this is very robust, but I think I think.
Yeah, because you have a strict inequality.
I mean, there's a lot of robustness here. I think it can get this. It's not important.
Okay.
I mean, the only thing that can happen if we close it, then. Oh, actually, I don't have strict inequality here. I think I could have a strict inequality here. With this definition, I actually get a strict inequality. It's like extremely robust. I think I want an open interval. Let's take it offline. It's not important at all.
Okay.
It's like super robust. I mean, I would be fine with S over 4 here.
Mm-hmm.
Right? Okay. So if I can do this, then I've proven the theorem. So let me tell you what the complexity measure is. So the complexity measure of C is going to be, I'm going to look at all left-hand sides F prime. This is a subset of F. This is a subset of vertices such that if I take all the sets of clauses in F prime, and I also throw in the filtering set E, then this implies C. What does this implication symbol mean? It means that any truth value assignment that satisfies this has to satisfy this. Okay. How do I know that this measure is finite, by the way? Well, the formula is contradictory. So if I throw in everything, then I imply whatever. Right? I mean, contradiction implies anything. So clearly the measure, okay, so let me tell you, the measure is size of F prime, where F prime is in F. Clearly this is at most the number of vertices, but it could be smaller. Just take any minimal subset of vertices. Note that I'm not counting the total number of clauses. I'm counting the number of sets of clauses. And I'm counting how many sets of clauses do I need to throw in, plus the filtering set to imply C. Take the minimal number, that's the complexity. I claim that this measure is a natural number, and that is well defined. How happy are we with this claim?
So it's like the minimal set of axioms that I need to derive from it.
It is, in particular, I could have derived C from, it's a minimal set of minimal number of subsets, such that thanks to these and the filtering set, I could have derived C. But I know that since I'm minimizing, from no smaller set could I've done it. Mm-hmm. So yeah, I'm kind of measuring. The idea is how much of the formula did I need in order to derive C? And the more I needed to derive C, the more impressive C is. Okay. Questions about this? Or let's maybe, I claim these three properties. Let's see if we can take them all. Axioms have very low complexity. I claim axioms have complexity 0 or 1. Why? Well, if my axiom is in the filtering set, then I mean I don't need anything. Then the complexity is 0. Otherwise, the axiom is living in some Fi. Well, pick that Fi. Okay. So check on that. I claim we also have subadditivity. Why?
that most the axioms.
No, so look at the complexity of these guys. So some, F1 and E is implying this guy, and some F2 and E is implying this guy. Okay, and now the resolution is sound, so clearly all I need here is F1 union F2. Maybe I can get away with less, but definitely this is enough.
And E.
And E. Yeah, but I'm not. Yeah. Okay. Sorry, that was plane B, right? Plane C is a little bit more fun. And now I am thinking about what to erase. I guess I'll have to go. Okay, it's getting late in the day, so I'll do a little bit of proof by picture, but I'm doing on like I'm not cheating you. I'm just sort of doing it pictorially, and then you can write down the details. So the way I'm going to prove C is I'm going to look at for any F prime in F, such that F prime has size at most S. I claim that F prime, I'm overloading a little bit now. This is now the conjunction of all the clauses in all the vertex sets, blah, blah, blah. F prime and E is in fact satisfiable. Okay, but note that the only way I can imply contradiction is by being contradictory, because otherwise, this means that any satisfying assignment here should also satisfy this thing, but contradiction has no satisfying assignment. So in order to get the complexity of contradiction, I have to plug in an unsatisfiable set here. If all sets of size at most S are satisfiable, that means that the complexity of contradiction is larger than S. So all I need to prove is this. Okay, and it's not a contradiction, it's not a coincidence that this S, I emphasize this, is the same as this S. Okay. So in particular, then fix P prime of actually let the size be exactly S. I mean, who cares? If you already had a smaller satisfying unsatisfiable set, then throw in more stuff. It doesn't become satisfiable. So now this is a set of vertices. Okay, so now let's maybe look down here. This is the whole graph. I'm below the expansion guarantee, so I know that the unique neighborhood of F prime is at least delta of the size of F prime. Number of vertices, I don't know what this is, but it's something positive. This is positive, this is positive, so it's bounded away from zero. It's not bounded away from zero even. Well, it is, but we don't care. It's positive. Okay? That means that there is some vertex set, let's call it VS, that actually, okay, let's say that this is all of F prime. There is a VS that is in the boundary. That is, it has a unique neighbor over here. Let me call that guy Fs. Note now that there must be a Vs that is in the neighborhood of Fs, but it's a unique neighbor of Fs. So it's not in the neighborhood of any other Fj. Right? So here they are. And now let me look at F prime minus Fs. Okay. Well, it's smaller than the expansion guarantee. So there is some unique neighbor, let's call it Vs minus 1, that has only one neighbor inside here. Let me call that neighbor, let me just rename if necessary and say that Fs minus 1 is that guy. Clearly Vs minus 1 is a unique neighbor, so it's a neighbor of Fs minus 1, but not of any earlier guy. So there are no, note that there are no edges from here to Vs. There are no edges from Vs minus 1 to here. Right? And just pictorially, you see that what will happen, dot, 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 let me go down to maybe for F2, when we have F2 and F1, F2 will have a unique neighbor V2, and F1 will have a unique neighbor V1. Let me write down the general condition. I'm finding V1, V2, V3 all the way up to Vs, such that the general condition is that Vi is a neighbor of Fi, but not of any earlier guy. I'm just using unique neighbor expansion, boundary expansion. Is this clear? This is sometimes referred to as a peeling argument. Okay. And now I claim that we're done. Clearly, this shows that F prime and E is satisfiable. Why? Well, with my excellent board technique, I've raised the resolution edge game, which is brilliant. But let's try to remember what it says. So basically, we're going to play. We start by playing on F1, V1. Okay. Adversary plays an epsilon 0 that satisfies E. What can I do? Well, I can modify V1 to satisfy F1. So we get alpha 1 such that F1 and E is satisfied. Because we win the edge game on this edge. Okay? Excellent. Suppose this was what adversary played, and now we are going to play the edge game on this, on F2, V2. So now we play on F2, V2. So we get an alpha 2 such that F2 and E is true. Right? By modifying only this. What happened to F1?
Nothing.
Nothing. Why?
Because we didn't have an edge.
Because no variables in here appear in here. If so, this would have been a neighbor of this. So actually, we're also satisfying F2, and we're not changing F1 because these variables don't appear in here. Okay, and now you kind of see what we're going to do. We're going to play on F3, V3. With the satisfier, we think of the adversary as playing alpha 2. And now we modify alpha 2 on V3, which is Vs minus 1, I guess. to get an alpha 3 that satisfies F3 and E. Okay? Just by flipping on this guy, we satisfy this. What happens to these two? Nothing, because these variables don't appear in here. Okay, keep going. This is the proof.
There's no problem with the overlap?
No, the overlap, I mean, if there was a variable, then it wouldn't be a unique neighbor.
Right.
Yeah, if X appears in, if there's an X that appears both here and here, then, I mean, the point is that
Right.
we know, just to point out that the point is that if J is less than I, we know that VI, and let me write this down like carefully. By the way I constructed the graph, and by the way I extracted the unique neighbors, I know this. Because if this were not true, I mean, if this was false, then there would be an edge from VI to FJ. But then it wouldn't be a unique neighbor.
Right, so in the actual graph, the BIs might overlap, but in this construction,
But in this construction, they won't, because of unique expansion. Okay. So I'll erase this quickly before you change your minds. And now we're almost done. Okay, let's see what we did. I claim we did C. No, yeah, I think this interval is okay.
I missed that C was strict, so yeah, it makes sense.
So okay, so we agree that we consider this. Okay, so then we just have left this. And I'm going to kick the can down the road a little bit by making another claim. Let's see what this claim is. So fix FC witnessing that fix FC, this is a left-hand subset of vertices of size sigma, witnessing that C has complexity sigma. Okay. Then, for all V in the unique neighbor set of FC, it holds that V intersect variables of C is non-empty. Okay. The claim is, okay, you're saying that C has complexity sigma, importantly less than S, so that we know that we have expansion. And fix any set. What does this mean? Let me write it down. Maybe this means that F, C, and E implies C. But I know that if I take any F that is in FC and remove it, then it does not imply C. Why? Well, if so, I would pick the smaller set. So fix any such, this is not necessarily unique. Fix one. Look at the boundary over on the right-hand side. Look at the variable sets. Now there can be overlap here, but I'm claiming that every variable set has at least one representative in C. Now I claim that we're done, because now the width of C now has to be, well, that's the number of variables in C, right? And this is, let's count. This is almost the size of this. I claim that every V has a variable in C. And what do I know about the size of this unique, this set of unique neighbors? Well, it's going to be sigma times delta, right? Except there might be double counting now. I mean, clearly some variables are maybe picking up the same variable. So how much am I overcounting here? At most L, right? I mean, the worst thing that can happen is that the V sets collude and they try to repeat variables as much as they can. But the total number, the multi-set of variables picked up here has this size. How often could I pick up any single variable in this multi-set at most this many times? And now, since sigma is at least S over 2, now we're done. If we can get this. So we only have this left now. Okay. So there exists, let's see. Okay, so, okay, good. Fix any V in the unique neighbor set and fix the neighbor FV, or FV in FC. Okay? This is a fancy F, this is a standard vertex set. Like the fancy guys are subsets of closed sets, this is just a closed. I know in particular that FC minus FV does not imply C, so there is an alpha such that alpha sets all of F fancy style FC minus FV to true. It sets alpha to false. And hence, it had better set FV to false also, because otherwise, I mean, we know that. Oh, and it sets E to true also. Alpha sets E to true. It sets this to true and this to true, but this to false. There must exist such an alpha witnessing the non-implication. This alpha had better set this guy to false, otherwise we would violate this. Okay. Okay, but now we play the edge game on FVV. That gives us an alpha prime such that alpha prime now satisfies FV. Right? What do I know about alpha prime on these other guys? Well, I know by assumption of the game that alpha prime also has to satisfy E. That's the rules of the game. What do I know about the rest of FC? Not affected, right? Because V is a unique neighbor of FV. So in fact, alpha prime satisfies FC and E. So alpha prime satisfies C, because otherwise we would have a violation here. But I only flipped variables in V. So some variable in V had better be in C. Otherwise the value of C wouldn't have changed. Now I claim we're done. Do I say this again? Takes like 1 minute to say it again, maybe. So again, I'm claiming that for a medium complex clause, somewhat high complexity, but below the expansion size guarantee, fix any set of vertices, fix any collection of subsets of clauses witnessing this complexity. That means that all the clauses in FC plus the filtering set together imply C. But as soon as I remove any vertex from FC, I have a non-implication. Okay. Fix any unique neighbor of FC. Here it is. Fix the unique neighbor FV. So the only places where variables in V occur in all of fancy style FC is in this subset. Now, since removing FV destroys the implication, there is an alpha that sets everything else to true, sets E to true, sets this to false, sets C to false. Okay? And now I just play on this edge. Alpha sets E to true, so that's a valid move for the adversary. I play my satisfier strategy. I get something back that satisfies both FV and E. And now, since V was all the variables in V occurred in FV only, they didn't occur in FC minus FV. So FC is still satisfied. FV is satisfied by the satisfier move. E is satisfied by the satisfier move. All of this is satisfied by the satisfier move. So whatever happened has also flipped C. But I only changed variables in V. So some of those variables were in C. Okay, so I think it's getting late. And now we're done. So now we have this theorem. And this is basically, I mean, this is not the way Ben-Sasson and Wigderson does it, but they do this 2 or 3 times. And then if you like look at what they do every single time, then basically what they do is this. Okay. And just as a sanity check, so now you can get, let me tell you about lower bounds you can get now. Sample random KCNF formulas over the satisfiability threshold. We know that a 3 CNF formula over n variables with, say, 5 times n clauses with some margin, that is unsatisfiable, like asymptotically almost surely. What is the graph sampled from this? This clause variable incidence graph. That is just a randomly sampled 5 regular bipartite graph. That's going to be an amazing boundary expander. Okay, so now you just take the clause variable incidence graph to be exactly like every clause is its own vertex, every variable is its own vertex. You have expansion, plug in this, and now we have Coatal-Semeredi in 1988. Exponential lower bounds for random KCNFs. Okay. For Tseting, what we're going to do is there's no filtering. For every vertex V in the graph, we're just going to take all the clauses, if you remember, that encode that the parity of the edges around V agree with the charge function. Okay, and every vertex at J is just going to be some edge variable, X edge. Okay, so basically I take a graph, and in that graph, I now make it bipartite by pulling out every edge. So basically, I'm going to have my Satin graph is over here, V1, V2, V3, V4. And now if you have different edges here, I'm not sure if I can do this. Let's say we have like V1, V2, V3, V4. Let's see if we can do this. This is edge 1, edge 2, edge 3, edge 4, edge 5. This is very improvised. Let me see. E1 as from V1 and V3, E2, V1 and V2, E3, V2 and V4, right? V2, I'm missing a 4, V4, no, wait, that was E3, yes. E4 is V3 and V4. E5 is V1 and V4. Okay. Suppose that this graph is an excellent edge expander. And in particular, look at what are the outgoing edges from V1, V3. Actually, it's nicer to draw. Let me draw it here. What are the outgoing edges from V1, V2? That's this edge, this edge, this edge, right? Let's see if this works. The neighborhood now is this, 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 this. And now you see, lo and behold, the outgoing edges, E1 is an outgoing edge, it's a unique neighbor. E3 is an outgoing edge, it's a unique neighbor. And E5 is an outgoing edge, it's a unique neighbor. E2 is not an outgoing edge, so it's not a unique neighbor. Okay, so if I have an edge expander and I like bipartize it, then I get a unique boundary expander. So I'm doing this a little bit quickly, but that's because we're running out of time. Basically, whatever edge expander parameters you have here, you inherit it from the bipartite expander. And now the question is, so if this is an edge expander, this graph is a bipartite expander. The only question is, can I win the resolution edge game? Okay, and the answer is yes, because suppose we're playing on this edge. Okay, another color. Suppose we're playing on V1, E1. Okay, there's no filtering set. So the adversary will play whatever, right? And then what do I need to do? Well, I need to satisfy this parity, which is a challenging task to be sure. But you know, I'm free to flip one of the edges. I think we can manage this. Okay. The pigeonhole principle version is similar, but I'm a little bit worried about time. I'm thinking about referring you to the notes. Let me just say one thing let me just repeat them maybe then that actually, even if you look in the notes, you will see that it works for the onto functional pigeonhole principle. So I take that, I say every pigeon gets a hole, but it gets exactly one hole. No hole gets two pigeon, but every hole gets at least one pigeon. That's the onto functional pigeonhole principle. Also known as the perfect matching principle, because basically I'm going to get a bipartite graph with n plus 1 vertices on the left, n vertices on the right, and the claim that there's a perfect matching. And what I'm going to do is I'm going to hit this graph with a random restriction, zeroing out most of the edges, but I'll make sure, just by counting argument, I'll get a left expander. Let me also make sure that there are no isolated holes on the right, which I can do. Okay, and then I already told you that for this graph, the Fi guys are going to be just pigeon axioms. The Vj guys are going to be all variables mentioning hole j. The functionality axioms, the hole axioms, the onto axioms, they all go into the filtering set. This graph that describes where the pigeons can go, it's going to be an expander, asymptotically almost surely. By the way I set up this graph, you get exactly the same graph, because the edges are the pigeons and the holes they go to. So it's not like, it's exactly the same graph. Okay, so it's going to be an expander. And now the only remaining question is, can I win the edge game? And the answer is yes, because if we're playing on some edge, suppose we're playing here, what the adversary needs to play a perfect matching of holes to pigeons. Because by the filtering set, the adversary has to play a perfect matching of holes to pigeons. And now there's one case, like look at this hole, and and either this pigeon already has some other hole, and then I don't care, then everybody is happy. But if this pigeon doesn't have a hole, then it's the only pigeon that doesn't have a hole, and some other guy, maybe this guy, is flying to this hole, but I have control over all of the hole variables. So I just say, sorry guys, you're not going to this hole, you are. And that I can do because I can flip all the variables related to this hole. Okay, and this okay, I promised that I wouldn't do the proof, and then I did the proof anyway, sorry about this. But this proves, just again, with this proves that I built now a resolution expander for the perfect matching principle, for the onto functional pigeonhole principle. And this gives us an exponential overlap, not only for, note that for Haken we did just the vanilla pigeonhole principle formula, but the argument I hand wave now, and that you find more carefully written up in the notes and in the scribe notes later, hopefully, actually works for the strongest possible pigeonhole. It's high time to wrap up. Any questions?
Is it like n+1 pigeons to n holes? Like that is simple.
It's okay, excellent. We haven't talked about this. It's important that it's going to be, this is going to give you something for n to the 2 minus epsilon pigeons and n holes. Because for n to the 2 minus epsilon, okay, and I raised that too, but basically the number, if I do this constant degree thingy, the number of variables is going to scale linearly with the number of pigeons, but it has to go down. Clearly, the width is at most the number of pigeons and holes. Sorry, the number of holes. So the width is at most n. I have a constant width CNF, so that's fine, but still n is the width upper bound. So in my enumerator, I cannot hope for better than n squared. I'm going to divide this by the number of variables and then exponentiate. So clearly, if the denominator is n squared, then I'm done. I'm dead. But as long as it's at most n to the 2 minus epsilon, I'm going to pick up n to the epsilon and get exponential in that. But all of the techniques we've talked about so far break down for n squared pigeons. And that's usually why you talk about the weak pigeonhole principle from the point of view of resolution and polynomial calculus. That's like n squared is an interesting bound. Now for resolution, as I've told you before, we can go above n squared all the way up to exponential, like arbitrarily large. In fact, if you think about it, you can have infinitely many pigeons, because if you mention more than 2 to the n pigeons, then if you mention that many pigeons, you're already using 2 to the n clauses, and I have a better bound. So even if I give you infinitely many pigeons, you're not going to use all of them.
Right.
Okay, so for any number of pigeons that you want to use, we actually have exponential overbound, exponential in cube root of n. This is by Razborov and Raz. For polynomial calculus, which we'll talk about starting on Thursday, we don't know anything, to the best of my knowledge, beyond n squared, which is very wrong. Other questions? Or comments? Good. Then I think this, again, just to repeat that with a few more minutes, we would have done all of lectures 2 and 3 with this technique. So why did we do the prosecutor-defendant game then? Well, we did it because, as you saw in the clique lectures, there are formulas for which we cannot prove lower bounds with this size-width relation for Ben-Sasson and Wigderson. There are formulas where the only way we know how to do it is actually by playing this game that characterizes resolution. But if you ever just want to, like, if you have one lecture and you want to do some resolution lower bounds, then probably just try to hand wave the Ben-Sasson and Wigderson size-width relation, and then probably not do this general framework, but instantiate it for like Satin or something, and just do the Satin lower bound. Okay, but that is it for today. Thanks.